In this video, we're going to be talking about comparing two populations or treatments, specifically inferences concerning the difference between two population or treatment means using independent samples. Now suppose that we have a population of adult men with a height of 71 inches and a standard deviation of 2.5 inches. And then we also have a population of adult women with a mean height of 65 inches and a standard deviation of 2.3 inches. And we assume that the heights are normally distributed. Now suppose we take a random sample of 30 men and a random sample of 25 women from their respective populations and calculate the difference in their heights. So the man's height minus the woman's height. So if we did this many times, what would the distribution of the differences be like? Well, here we see that we have a distribution of male heights with our mean of 71 and our standard deviation of 2.5, and our distribution of female heights with a mean of 65 and a standard deviation of 2.3. Now notice that when we take repeated samples of size 30 from the population of male heights and calculate the sample means, we have the sampling distribution of x bar sub m. Again, our mean is 71, and here we see that we have a standard deviation of our sample mean for males as 2.5 divided by the square root of 30. Now, supposing that we were to take repeated samples of size 25 from the population of female heights and calculate the sample means, we would have the sampling distribution of x bar sub f, with still a mean of 65 and a standard deviation of our sampling distribution for females as 2.3 divided by the square root of 25. So if we randomly take one of the sample means for the males and one of the sample means for the females and find the difference in the mean heights, doing this repeatedly will create the sampling distribution of x bar sub m minus x bar sub f, which gives us a standard deviation of our x bar sub m minus our x bar sub f. Notice here that we're just taking the standard deviations and squaring them separately, adding them together, and then taking the square root of that sum. So describe the sampling distribution of the difference in mean heights between men and women. Well, the sampling distribution is normally distributed with a mean of our sampling distribution of m minus our sampling distribution of f of 71 minus 65, which equals 6. And our standard deviation as the square root of 2.5 squared over 30 and plus 2.3 over 25 squared, or excuse me, 2.3 squared over 25. So what is the probability that the difference in mean heights of a random sample of 30 men and a random sample of 25 women is less than 5 inches? So if we take a look at that, this is what we're looking for, that left tail. So the probability of our x sub bar sub m minus our x sub bar sub f is less than 5 is 0.0614. Let's look at the properties of the sampling distribution of our x bar sub 1 minus our x bar sub 2. Now if the random samples on which x bar sub 1 and x bar sub 2 are based are selected independently of one another, then we're able to say that the mean of our x bar sub 1 minus our x bar sub 2 will equal the mean of x bar sub 1 minus the mean of x bar sub 2, or the mean sub 1 minus our mean sub 2. And so this is our mean value of our x bar sub 1 minus our x bar sub 2. The sampling distribution of x bar sub 1 minus x bar sub 2 is always centered at the value of mu sub 1 minus mu sub 2. So x bar sub 1 minus x bar sub 2 is an unbiased statistic for estimating mu sub 1 minus mu sub 2. Our second property is showing that the variance of our x bar sub 1 minus x bar sub 2 is that the variance of the differences is the sum of the variances. and that our standard deviation of the differences is the square root of the sum of the variances. And a third property is that in n sub 1 and n sub 2 are both large, or the population distributions are at least approximately normal, then our x bar sub 1 and our x bar sub 2 each have at least approximately normal distributions. This implies that the sampling distribution of x bar sub 1 minus x bar sub 2 is also approximately normal. The properties for the sampling distribution of x bar sub 1 minus x bar sub 2 implies that x bar sub 1 minus x bar sub 2 can be standardized to obtain a variable with a sampling distribution that is approximately the standard normal z distribution. When two random samples are independently selected and n sub 1 and n sub 2 are both large, or the population distributions are at least approximately normal, the distribution of z, which is our x bar sub 1 minus x bar sub 2 minus our mu sub 1 minus mu sub 2 divided by the standard deviation of our differences, is described, at least approximately, by the standard normal z distribution. We must know that our sigma sub 1 and our sigma sub 2 values are in order to use this procedure. So again, we need to know what our standard deviations are for our first and second populations in order to use this procedure. Because if our standard deviations are unknown, then we're going to need to use a t distribution. Let's talk about some two-sample t-tests for comparing two populations. So our null hypothesis would be that our mu sub 1 minus mu sub 2 is our hypothesized value. The hypothesized value is often 0, but there are times when we are interested in testing for a difference that is not 0. Our test statistic would be t equals our x bar sub 1 minus our x bar sub 2 minus the hypothesized value divided by the square root of our s sub 1 squared divided by n sub 1 minus our s sub 2 squared divided by n sub 2. Now the appropriate degrees of freedom for the two-sample t-test is going to be this equation here, where our v sub 1 is our s sub 1 squared divided by n sub 1, and our v sub 2 is our s sub 2 squared divided by n sub 2. Now it's important here to know that the computed number of degrees of freedom should be truncated to an integer. So truncated would mean rounding down. So if we got 15.7, we would round down to 15. If we had 15.3, we would round down to 15. So a conservative estimate of the p-value can be found by using the t-curve with the number of degrees of freedom equal to the smaller of n sub 1 minus 1 or n sub 2 minus 1. So you don't really need to freak out about this equation here, and your calculator should be able to help you out as well with that. So our alternative hypothesis would be our mu sub 1 minus our mu sub 2 is greater than our hypothesized value, and there the p-value would be the area under the appropriate t-curve to the right of the computed t. If our alternative hypothesis was mu 1 minus mu 2 is less than the hypothesized value, then our p-value would be the area under the appropriate t-curve to the left of the computed t-value. And if our alternative hypothesis was that mu 1 minus mu 2 did not equal the hypothesized value, then we would have 2 times the area to the right of the computed t if we had a positive t, or 2 times the area to the left of the computed t if we had a negative t. So what's another way to write our hypothesis statements? If we have our null hypothesis, mu 1 minus mu 2 equals 0, so when we have that hypothesized value of 0, we can rewrite these hypothesis statements this following way. Mu 1 equals mu 2 We can say that our alternative hypothesis, instead of mu1 minus mu2 is less than 0, we can then say mu1 is less than mu2. Instead of saying mu1 is minus mu2 is greater than 0, we would say mu1 is greater than mu2. And if our alternative hypothesis was that mu1 minus mu2 did not equal 0, we would also be able to say that it was mu1 did not equal mu2. It's important to make sure that you define both mu sub 1 and mu sub 2. So what assumptions do we need to think about here? First, the two samples are independently selected random samples from the population of interest. Second, the sample sizes are large, generally 30 or larger, or the population distributions are at least approximately normal. Now, when comparing two treatment groups, you want to use the following assumptions. First, that the individuals or objects are randomly assigned to treatments, or vice versa. And second, that the sample sizes are large, so generally 30 or larger, or that the treatment response distributions are approximately normal. Let's take a look at an example. Are women still paid less than men for comparable work? A study was carried out in which salary data was collected from a random sample of men and from a random sample of women who worked as purchasing managers and who were subscribers to Purchasing Magazine. Annual salaries in thousands of dollars appear below, and the actual sample sizes were much larger. So we're going to use an alpha of 0.05 to determine if there is convincing evidence that the mean annual salary for male purchasing managers is greater than the mean annual salary for female purchasing managers. So the first thing we want to do is state our hypotheses. So our null hypothesis is that mu sub 1 minus mu sub 2 is 0, and our alternative hypothesis is that mu sub 1 minus mu sub 2 is greater than 0, where our mu sub 1 is going to be the mean annual salary for male purchasing managers, and our mu sub 2 is going to be the mean annual salary for female purchasing managers. So we're saying our null hypothesis is that there is no difference, and our alternative hypothesis is implying that men are paid more. Now, if we had defined mu sub 1 as the mean salary for female purchasing managers and mu 2 as the mean salary for male purchasing managers, then the correct alternative hypothesis would be the difference in the means is less than 0. So it really all depends on how you define your mu sub 1 and your mu sub 2. So now we're going to verify our assumptions. Given two independently selected random samples of male and female purchasing managers, so we're good there. Now, even though these are samples from subscribers of Purchasing Magazine, the authors of the study believed it was reasonable to view the samples as representative of the populations of interest. Second, since the sample sizes are small, we must determine if it's plausible that the sampling distributions for each of the two populations are approximately normal. Since the box plots are reasonably symmetrical with no outliers, it's plausible that the sampling distributions are approximately normal. So now we're going to compute the test statistic and our p-value. So we'll plug in for our t, giving us a value of 3.11. And to find the p-value, we first need to find the appropriate degrees of freedom. So we can plug that into our formula, and we get 15.14. Remember, we're going to truncate or round down this value, so that would become a 15. So now we're going to find the area to the right of t equals 3.11 in the t-curve with a degrees of freedom of 15. Which is going to give us a p-value of 0.004. When we compare that with our alpha, we see that our p-value is less than our alpha. So since the p-value is less than alpha, we reject our null hypothesis. There is convincing evidence that the mean salary for male purchasing managers is higher than the mean salary for female purchasing managers. Now, what potential type error could we have made with this conclusion? A type 1 error. The two sample t confidence interval for the difference between two population or treatment means. For that, we're going to have our general formula for a confidence interval for our mu sub 1 minus mu sub 2. When the two samples are independently selected random samples from the populations of interest, and the sample sizes are large, so generally 30 or larger, or the population distributions are at least approximately normal, is going to be our x bar sub 1 minus our x bar sub 2 plus or minus our t critical value divided or times the square root of s sub 1 squared divided by n sub 1 plus s sub 2 squared divided by n sub 2. The t critical value is based on our degrees of freedom, where our v sub 1 again equals our s sub 1 squared divided by n sub 1, and our v sub 2 equals our s sub 2 squared divided by n sub 2. And our degrees of freedom should be a truncated to an integer. For the comparison of two treatments, you use the following assumptions. 1. That individuals or objects are randomly assigned to treatments or vice versa, and that 2. The sample sizes are large, so generally 30 or larger, or the treatment response distributions are approximately normal. Let's look at another example. In a study on food intake after sleep deprivation, men were randomly assigned to one of two treatment groups. The experimental group were required to sleep only 4 hours on each of 2 nights, while the control group were required to sleep 8 hours on each of 2 nights. The amount of food intake on the day following 2 nights of sleep was measured. So we're going to compute a 95% confidence interval for the true difference in the mean food intake for the two sleeping conditions. So here we see our data, and we want to find the mean and standard deviation for each treatment. Doing so, we see that we have an x bar sub 4 for 4 hours of sleep of 3,924 and an s sub 4 of 829.67. We have an x bar sub 8 for our 8 hours of sleep of 4,069.27 and our s sub 8 as 952.90. So now we're going to verify our assumptions. Men were randomly assigned to two treatment groups. The distribution of normal responses of the normal response distributions is plausible because both box plots are approximately symmetrical with no outliers. And now we're ready to calculate our interval. So we'll plug in our values. And so here we'll see our x bar sub 4 minus our x bar sub 8 plus or minus our t critical value divided by our sample standard deviation squared divided by 15 plus our sample standard deviation of the 8 hours divided by 15, giving us a negative 814.1 and a 523.6. So now we want to interpret this in terms of our context. So we'll interpret our interval in terms of our context. So we are 95% confident that the true difference in the mean food intake for the two sleeping conditions is between negative 814.1 and 523.6. Now, based on this interval, is there a significant difference in the mean food intake for the two sleeping conditions? And we're going to say no. Since 0 is in that confidence interval, there's not convincing evidence that the mean food intake for the two sleep conditions are different. Now we're going to talk a little bit about a pooled t-test. It's used when the variances of the two populations are equal. So our sigma sub 1 will equal our sigma sub 2. It combines information from both samples to create a pooled estimate of the common variance, which is used in place of the two sample standard deviations. And when the population variances are equal, the pooled t procedure is better at detecting variations from our null hypothesis than the two-sample t-test. But it is not widely used. In fact, it's rarely used due to its sensitivity to any departure from the equal variance assumption. P-values computed using the pooled t procedure can be far from the actual p-value if the population variances are not equal. Hence one of the reasons why it's not widely used.